Okay, a video on 10.1 parametric curves. We already did some work on this back in chapter 3, but let's go. So remember, with parametric curves, we have x and y defined in terms of t. So dy dx, which is our important derivative, is equal to dy dt over dx dt. This will become second nature. And then the second derivative, d squared y over dx squared, pay attention to this. It's the derivative with respect to t of dy dx divided by dx dt. So it looks like this, but that causes a little confusion. But let's see how it plays out with examples. So here's a classic example. X equals t squared minus 3t, y equals t cubed. You're asked, what is dy dx? Well, it's dy dt, which is 3t squared, over dx dt, which is 2t minus 3. Now, when we go to calculate the second derivative, I need to take the derivative with respect to t of this, which is the quotient rule. All these rules better be reviewed, which is 2t minus 3 times 6t minus 3t squared times 2 over 2t minus 3 squared. But then I have to divide that by dx dt, which is 2t minus 3. So you could simplify this one and say it's equal to this divided by 2t minus 3 cubed. I'm not that interested in that. So now let's go to one with trigonometric functions. X equals tangent t, y equals secant t. dy dx would be dy dt, which is secant t tangent t, divided by dx dt, which is secant squared t. That reduces to tangent t over secant t, which you should and must know is equal to sine over cosine divided by 1 over cosine, which gives you sine t. To get the second derivative, I then take the derivative of dy dx with respect to t, that's cosine t, and I divide it by dx dt, which is secant squared t. So your second derivative is equal to cosine cubed of t. All right, we're halfway done, 10.1. Hang in there. Now, this will be a nice review of something you've done already, arc length. Now, if you remember with our traditionally defined functions, y equals f of x, the length of this function from a to b was the square root of 1 plus dy dx squared inside the square root of that times dx. I'm not going to go through the derivation of that. But if you look at that, square root of 1 plus dy dx squared. For parametric, it's very similar. All you have is the length from a to b of the square root of dx dt squared plus dy dt squared dt. So, example, x equals 1/3 t cubed, y equals 1/2 t squared. I have to tell you where I'm going from 0 to 1, and the length would be from 0 to 1 of the square root of what is dx dt, it's t squared, so I'd have t squared squared, and dy dt is t squared dt. Now this would be a very good one. You guys have really got to start getting good using fn int, but I would solve this using fn int by putting math 9, put in my 0 to 1, put the function in, and I get this decimal, 0.60947. That's just an approximation. And I'm going to start drilling into your head that for the AP, they only want 3 decimal places, so your final answer would be 0.609. So if this was a free response question, you'd probably get a point for having the proper integrand. You'd have a point for having the proper limits of integration, and then you have a point for putting it in your calculator correctly. All right, last thing in 10.1. Well, we're only at 5 minutes and 14 seconds, nothing. Now you're going to be asked also with questions like this. Find the lowest point of this parametric curve, x equals t plus 1 and y equals t squared plus t. Now let's think about that. Lowest or highest point, when they were defined as y equals f of x, you take the derivative, set it equal to 0, because you were calculating dy dx. But now I have a parametric curve. But the way you have to think of parametric curves is x and y are defined independently. So if I'm looking for the highest or lowest point, the only thing I'm worried about is the y. So what I do is take dy dt equal to 2t plus 1, set it equal to 0, which happens at t equals negative 1/2. So then I set up, remember sign charts? All this stuff coming back. To the left of negative 1/2, this is negative. To the right, it's positive. Therefore, this is going to be a min. So, the min occurs at t equals negative 1/2. Now, they're asking you what's the lowest point. You have to go back in and substitute for x. If t equals negative 1/2, x is going to equal 1/2. Y will equal negative 1/4. Now the other thing I did as a review with parametric is you should be able to plot these graphs to see what they look like. So if I have the interval negative 2 less than or equal to t is less than or equal to 2, and I want to look at what this curve looks like, I can just put in negative 2 for t. I'll get x equal to negative 1 and y equal to 2. You see, so I plotted that point. The next point I do, most likely, would be negative 1. X would be 0, and y would be 0. You see this point here. Next point would be x equal to 0. T equal to 0, I'd get 1, 0. That's this point. And then if I did t equal to 1, I'd get 2, which is here. So this curve is going like that. And you see we found the lowest point here. Only looking at, the important thing here is dy dt. So another question might be, what is the rightmost or leftmost point on a parametric curve? And there, all you would deal with is dx dt, and I would set that equal to 0 and solve from there. That's it.